Welcome back to part 5, which is the last section of this chapter where we talk about aqueous ionic equilibrium and buffers and their role in acid-base reactions. In this section, we're going to talk about titration of strong base, strong acids, and titration of weak acids and strong bases. We're going to look at molar solubility. And we're going to compare Q and K to see if we are at equilibrium or not. So all ionic compounds will dissolve in water to some degree, but many of them are super low solubility. That is, they're so low in solubility that we call them insoluble because we don't see any evidence of any of it going into solution. So we can apply the concepts of equilibrium to this concept, and in this we call this the equilibrium constant K sub SP. Okay, and so this is the solubility product constant of aqueous type materials. So the solubility product constant K sub SP is calculated just like we've seen the others. You only use aqueous. So usually in these we're starting with a solid of some type, so that doesn't play any role. We're just looking at how much of it will be soluble or how much it dissolves in there. So our example here is that if we have lead chloride as a solid and we put it in water and it solubilizes into lead ion and chloride ion, 2 chloride ions, the KSP, just like we've been writing these K expressions, is going to be the lead, concentration of the lead times the concentration of the chloride squared because we're taking the coefficient. And so here's a list of these, and again, I'm not taking a super long time to describe it because we've already talked about this in different Ks, Ka, Kb, Kc, now we got KSP, but they're all basically the same thing. This one though specifically, we're using it to decide if something will dissolve in water or not. So that brings us to a concept called molar solubility. Solubility is the amount of solute that will dissolve in a given amount of solution at a temperature. So usually you see them at 25 degrees C. That's pretty standard. Molar solubility is how many moles of solute will dissolve in 1 liter of solution. Okay, so it's the molarity of the dissolved solute in a saturated solution. Saturated meaning we put all of it we can in there, and anything else that goes in there, it's going to precipitate out. Now, the molar solubility equation is this right here, okay? And you're welcome to use this to calculate it, but really what I usually do is I'm going to be just using the ICE table and solving for X like we did before. And so I'll show you a little bit of what I mean in 17.8. So lead chloride, now the things that have solubility in these problems are going to be the solids that we're dissolving, okay? So the KSP for lead chloride is going to be 1.17 times 10 to the minus 5, so that's very small. All right, we always like it when we see those very small ones. And so if I want to calculate the molar solubility, I'm going to solve for X. Just solve for X like we've been doing the whole time, okay? So I have lead chloride solid in equilibrium with lead 2 plus aqueous plus 2 Cl minus aqueous. So my KSP is going to be equal to 1.17 times 10 to the minus 5, which is equal to the lead times the chloride squared. All right. So if I do an ice table for the, oh, I've already got it over there. I start out sorry, with nothing, because these are the products, and then I go up plus S, or I still use X honestly, or up to S or 2X. So I'm going to change those because that's what I use X's, because it's just easier. All right, and so then I've got X and 2X when I get done. So that's my equilibrium concentration. So my KSP is going to be 1.17 times 10 to the minus 5. This should look very familiar. Times X times 2X squared. All right. So X times 2X squared. Remember, you're squaring this whole thing, right? So that's going to be X times 4X squared. That's going to be 4X cubed, and that's still equal to 1.17 times 10 to the minus 5. All right, so I've got a 4 over here, which is a real number. I've got to get rid of that. So I'm going to divide my 1.17 by 4, and I'm going to get 2.925 times 10 to the minus 6, and that's going to equal X cubed. And so to get rid of my cube, I'm going to take the cube root of both sides, and the cube root of X cubed is X, and the cube root of 2.925 times 10 to the minus 6 is 0.0143 molar. So that is X, and that is the molar solubility. And you might want to just do it 1.43 times 10 to the minus 2 molar if you want to. So I prefer doing the molar solubilities like this rather than using that formula, because I already know how to do this. And it's like by the end of this chapter, you've done this so many times, it's like second nature. So, and there's U1 to do for iron hydroxide. Now, one thing that will affect the solubility of a solute in a solvent is if I add a common ion. The addition of a soluble salt that contains one of the ions of the insoluble salt decreases the solubility of that insoluble salt. So if I add a soluble salt that, like, my example down here in a minute is going to be NaF, I think. But if you add sodium chloride, okay, which is very soluble, right, that's table salt, to the solubility equilibrium of lead chloride, which we know is not very soluble, okay. So what that's basically I'm doing is sodium is going to be a spectator, okay. It's going to be on both sides. But I'm adding chloride. And so if you remember from Le Chatelier, if I have chloride in my product side and I add chloride, I'm going to shift that equilibrium to the left. And which means it's going to shift it towards the solid form, which is going to make it even less soluble than it was. So what is the molar solubility of CaF2 in a solution containing 0.1 molar NaF? All right, and the KSP for CaF2 is 1.46 times 10 to the minus 10. So it's already not very soluble at all, right? So what I'm going to do is I'm going to figure out what is the molar solubility. What is the molar solubility if I also add 0.1 molar NaF? So I start out with the CaF2, and under normal circumstances I have 0 and 0, but I'm saying I'm going to add 0.1 molar NaF at the beginning. Okay, I'm adding a little bit of that, and so I'm going to go ahead and write this for you so we can kind of see. Okay, so that's what it looks like when it forms ions, right? So that's why it's plus X and plus 2X. Okay, because I got a 2 there. And so I'm ending up with X and 0.1 plus 2X. Now, I've already seen that my KSP is 10 to the minus 10, which is super small, so I'm not going to have to worry about that minus 2X, right? So when I put this in here, my KSP, which is 1.46 times 10 to the minus 10, is going to be equal to the Ca2 plus times the F minus squared. Okay? And so that's going to be equal to X times 0.100 squared. Oops. So 1.46 times 10 to the minus 10 is equal to 0.0100x. So x is equal to 1.46 times 10 to the minus 10 divided by 0.0100. So x is equal to 1.46 times 10 to the minus 8. And that is the molar solubility. All right, simple as that, okay? Very, very simple. So again, you can try to use that formula for molar solubility, but it's so much simpler to do it this way. All right, and then there is one with calcium fluoride and calcium nitrate. So once something has reached its solubility mark, it's gone past its molar solubility, then it's going to precipitate. And we saw precipitation reactions in Chem 1, and that's where you put two liquids together and you form a solid, right? So precipitation occurs when the concentrations of the ions exceed the solubility of the ionic compound. And so we can run Q to see if it's going to be saturated, unsaturated, or above saturation. Now please note, Q is less than KSP, it's going to be saturated and there's no precipitation, okay? If Q is less than KSP, it's going to look the same. It's unsaturated with no precipitation. Once you get past that point, whatever it is, okay, that KSP, then above that, it's going to be above its saturation level, and so it's going to precipitate out. So if you do this, you should be able to figure out if it is all the way to its solubility or not. Has it reached its molar solubility or not, by using whatever the situation is that it describes for you. All right, so the other criteria is that some solutions that are above saturation won't precipitate until you disturb them somehow. These are called supersaturated solutions. And the way you make a supersaturated solution is you heat it up. So you're really you're putting solute in there at a higher temperature than what the tables dictate. And then if you slowly let it cool off, that stays in solution. And then if you touch it, it will all of a sudden show all of those solids in there. Okay, so this is a standard where you've added two liquids together in this case, sodium nitrate and sodium chromate, and then you form silver from silver nitrate and sodium chromate. You form silver chromate, and it precipitates out as the silver chromate, which is really cool looking. Looks like a lava lamp. Your supersaturated is you heated it up so it would take more solute than it should, and then you put one little crystal in there, and it will do this lovely little explosion looking of crystals in there. And this is how you do those crystal gardens, if you've ever done those. You do supersaturated solutions, and then you seed them, and then the precipitate will actually grow from the bottom. So that's, if you've never done those, they're really fun. They're called crystal gardens. So we have a solubility table, and this we used this way back in Chapter 8 when we were looking at solubility in Chem 111. And so I just brought this back up to remind you we had all these rules about what would and what wouldn't, and we said it's insoluble, remember? But now we know that it really is soluble, but it's just not very soluble. And so you can't really use this soluble-insoluble table anymore now that we know how to use the rule of Q for this. So we have a solution of lead 2 nitrate, and it's mixed with a solution containing sodium bromide, and we form a solution that is 0.0150 molar lead nitrate and 0.00350 sodium bromide. And they want to know, does a precipitate form in the newly mixed solution? And so all you're going to do is you're going to run the KSP calculation, but we're running it at Q because we don't know if it is actually at the molar solubility or not. So we know that, so this is going to be lead 2 nitrate plus sodium bromide gives us lead bromide plus 2 NaNO3, so that's going to give us 2 there. Okay, so that's your balanced chemical equation for this. Now in these you're going to have to balance that equation so you know what your coefficients are if you're not given that equation. Alright, so that's going to be the first step on these when you're running Q. Alright, so we know the KSP for this would be the PBBr2. Alright, so what's kind of a better thing to do is look at it and see what ions you're looking at. And so really what we're looking at is lead and bromine, because remember, sodium and nitrate are going to be present in the same, basically the same forms. So they're going to be spectators. And so you can write PBBr2 and NaNO3, but really what you're looking at is, PB and Br. So you're really looking at the Pb2 plus 2 Br minus. Does that make sense? Because these are spectators. So they just brought your solids in, or your liquids in, so that you could do this calculation. So the lead times the bromine squared, right? Because we have 2 bromines. So that's really going to be your KSP. All right, so everybody understand that? We're doing this plus this, and then we're producing ions because we're putting it in water. All right, and then this NaNO3 is going to be found on both sides. So that's why it's a spectator. So you got KSP would be lead times the bromine squared. So then we're going to find Q. So Q is also the same exact calculation, right? So we just plug our numbers in. So we are going to have 0.015, which is your lead, times 0.00350 squared. And so when you multiply that, you're going to get 1.84 times 10 to the minus 7. Now, once you get that number, okay, that you need to compare it to the known KSP, and the known KSP for PBR2 is 4.67 times 10 to the minus 6. So Q, so 1.84 times 10 to the minus 7 is less than 4.67 times 10 to the minus 6. So Q is less than KSP. So that means that it hasn't reached this level yet. So there's no precipitate. There's no precipitate because it's not saturated yet. It would have to be equal to this to be saturated, and it would still have no precipitate. It has to be above that. Okay? So since Q is less than KSP, then there is no precipitate. If it was higher than that, a precipitate would form. And so I have given you a practice to do that as well. And that's it. So we are done. Put a fork in us.